I'm going to talk to you a bit today about the isotopic record of the geobiological record, or the geochemical record, somewhat what Lucy was talking about. And I will preface this that I am by no means an expert in isotopic chemistry, but I'm the best you've got for this warm-up talk. So I will try to answer any questions that you have after this, but some of the questions might best be kept for the speakers. So this is actually going to be just a short talk, since this is a huge sort of topic, and it's essentially a detective story where you look at a signal and then you try to interpret it and figure out the best that you can make of it. So I'm just going to familiarize you with the different types of isotopic fractionation and the terminology that's used, as it's quite oftentimes foreign from what we are used to seeing. So first things first, just in case, as Sarah has pointed out earlier, oh, I guess I should be doing this too. Yeah! Not everybody, never assume that your audience knows exactly what you're talking about for the most basic stuff. So just in case you don't know what an isotope is, I'm just going to cover that quickly. So when atoms are formed, either through decay of other atoms or initially formed at the creation of the atom back in the stellar days of matter, you can form atoms with the same number of protons, but different neutrons. And so here's an example of carbon. All of these have 6 protons, but they have different various numbers of neutrons, and so you can get carbon of a weight of 12, a weight of 13, or a mass of 14. And so you have 3 different prime forms of carbon out there, for example. And carbon 12 and carbon 13 are stable, as in they don't decay to other forms of atoms, to lesser atoms, on an appreciable time scale. But carbon 14 is radioactive, has a half-life of 5,700 years. So if you have like a pound or a mole of carbon 14, after 5,715 years, you will have half a pound or half a mole of carbon, as it will have degraded to other products. So primarily in the geochemical record, since we're looking at timescales of 4 billion years and 3 billion years, we're typically focused on the stable form of isotopes that we have. The heavier isotopes are typically the less stable ones, so you're looking for the ones that mostly are near the mass of the base atom. And the differences in the geologic record between the ratios of these isotopes tells a lot about the environmental and biological conditions that we have. So, before we get into the talk, I have to address this. So there is a special sort of terminology that isotopic scientists use, and it is this delta notation. And so if you look at any isotopic paper, they're going to refer to the delta values for the isotopes. And that is essentially, you take however much of the heavier element, and so in this case carbon 13, and you find a ratio between carbon 13 and carbon 12 in the sample. And then you subtract it from a ratio in a standard sample that has been established unilaterally, so you always are comparing to the same value in the literature. And then you divide that difference over that standard reference again. And so you multiply it times 1,000, and you get this delta value. And so this is reported as either delta or per mil, using this symbol, which looks like a typo of a percentage symbol, but that's actually what it looks like. And so 1% of a composition of something is equal to 10 delta, or 10 per mil. And apparently this is a point of contention amongst isotopic scientists, that you refer to it as delta or per mil instead of del. Apparently that's like nails on a chalkboard for a lot of people. So they've actually, I found this in my studies, they have this poem. There once was a man from Cornell who pronounced every delta as del, but the spirit of Uri returned in a fury and transferred that fellow to hell. So remember that, delta and per mil. So the reference standards that I pointed out before, this is what's been established in the geochemical community. And if I'm mistaken, you can take it up with the either Wikipedia or the isotope geochemists to follow me this afternoon. But the reference standards for the carbon ratios come from this Vienna PD belemnite.
Very good.
All right. From South Carolina. Nitrogen, they just fix it to our current ratio of nitrogen in the atmosphere. Hydrogen and oxygen, since the ocean is a great sort of bulk area, its ratio does not change much. So they fix that standard to the modern mean ocean water value. And sulfur, this one's always a bit intriguing to me, and I wish I knew why. They fix it to this meteorite sample from Canyon Diablo. I don't know, it must be a popular one, or there might be some legitimate scientific reason for it, but that is what that is fixed to. So there are 3 different types of fractionation that I'm going to touch upon here. The first one is equilibrium fractionation. Since when you're looking at samples in the rock, they'll have different ratios, and in order to understand how they get to that ratios, you have to understand the processes that go into fractionating them between the heavy and the lighter isotopes. So equilibrium fractionation involves separation of the isotopes based upon an equilibrium process. So if you have a chemical reaction going in some water and they're exchanging atoms between them, there might be a tendency for one of the sides of the equilibrium reaction to scavenge up the heavier isotopes, for example. And so you will see a definite signature between the heavy and the light products and reactants in this reaction based upon just equilibrium processes. And this is dependent upon larger atoms, the heavier isotopes, typically have a decrease in their vibrational energy, and so that affects what side of the equilibrium equation they'll show up upon. And so an example of this, not 100% of the time, but a lot of the time, is water condensation. So if you have a room at 100% humidity and you have some water droplets that form, it is freely exchanging between the water moisture in the atmosphere and the water moisture on the surface. And so the heavy isotopes in the drops that are forming, as long as that 100% humidity is maintained, will precipitate more readily, and so the water in those droplets will be heavier than the water in the air. A second type of fractionation is kinetic fractionation. And so this is the other type of processes that occur during non-equilibrium conditions. And so that would be if you had wind blowing through that previous experiment and it wasn't 100% humid anymore, and you're going to get still some water condensation, or actually, let's look at this in the reverse manner, sorry. As I have down here, evaporation is typically a process. So you'll have water that has reached a high enough temperature to kick up some of the water into water vapor. And the heavier elements will be left behind, and the lighter elements are preferentially kicked into the water vapor. And then wind blows through, and it blows out those lighter elements, making it a non-equilibrium condition, which then encourages more of the lighter elements to come into the air and then pulled away. So that's an example of a kinetic fractionation process. And another major thing here is biological processes are typically not at equilibrium. So they're driven in one direction and have a very hard time going backwards. And so you see a large preference for lighter isotopes in biological processes. And this is one of the major line of evidence that they look at for the biosignatures that Lucy was talking about before. If you see something that looks like life, you can take an isotopic ratio from it and see if it corresponds to the environment of what you would expect, or if it's enriched in light isotopes, or if it's enriched in one direction, then it's indicative of a biological process. And so that's some of the things that they've used for some of the rock samples from Greenland from 3.6 billion years ago, as to try to support the evidence that the samples they're looking at are from living matter. And so all of this together in a nice, pretty diagram. So if you look at the ocean as a base value, of 0%. So that's our reference material. And you're looking at the oxygen, the heavy oxygen, as it goes throughout your environmental system. It first starts with evaporation. Lighter isotopes evaporate, and so suddenly you have the clouds up there that are at -10 delta or -10 per mil. And so you now have clouds that are isotopically lighter than the ocean. Then, when they head over the land, it starts to rain. You preferentially rain the heavier isotopes. And so now you get, it's only -3 per mil now. And the water vapor up here is then -15 per mil. And so you get lighter elements down here, which is at the same time enhancing the water that's left behind. And then you can get evaporation, returning it to the system, which helps to make it lighter again, and the vapor passes on. You can cross over some mountain ridges, and the subsequent precipitation then changes the ratio again. So you can track how the fractionation changes throughout this ecological system. And it tells you some evidence where the water came from, what happened to it along the way. It just leaves some signal behind that you can put your detective hat on and help to figure out what is going on. The last type of isotopic fractionation I'm going to talk about is mass independent. And so this is stuff that's not the kinetic isotopic fractionation that I talked about before, or the unidirectional one. So this is not based upon mass for the fractionation. So this, it's not based upon the mass, so it doesn't scale linearly like it did with the equilibrium and kinetic fractionation. This is based on photochemical and spin-forbidden reactions. And so you'll see some signals that are left behind due to the isotopic fractionation that is not covered by the previous forms that I mentioned. And I'll get to a picture in just a second that'll be quite informative. But one of the best things that they use to track this with is sulfur isotopes. And so when you look at a graph like this, so this is a display of sulfur isotope fractionation throughout the Earth's geologic history. And if you look at this, you can see a giant scatter plot over here, and then suddenly it all evens out and is level for the past 2.5 billion years. And so I hope if you're a scientist or anybody and look at this, you can be like, something has happened there. Let's figure out what that is. And so this corresponds to the great oxygenation event, which the oxygen reacts with the sulfur in the isotope to create sulfates, and the sulfate-reducing bacteria then essentially fixes this isotopic ratio after this. But before then, it doesn't have the oxygen to react with, and nothing essentially scavenges out. So you see this, what appears to be random sort of fractionation that's going on. So you can track the isotopic record and see really great things that help to tell us about what's happened in the history of the Earth's geologic record. And so the main take-home point, and I will let you choose your geek of choice, whether you want Fringe or Buffy the Vampire Slayer, is you get to put on your detective hat and use it to figure out what this record is telling you. And so the high delta values equal heavy isotopic enrichment, and anything else that you see different with the isotopic record could be because of the temperature, the different chemical reactions that have been happening, precipitation, or other processes that scientists are currently discovering. But it's a great tool. You just have to spend a lot of time and figure out why the ratios are the way that they are. So that's isotopic fractionation in a nutshell.